Okay, hi to everybody in my Algebra 2B classes. Hope that you're good, hope that you're healthy, hope everybody in your family's healthy. We're going to talk about trig functions and the unit circle and how those two ideas are connected. Because when you think about trig functions, you're probably thinking about triangles. So because of that, we are going to start with a triangle. And this is a right triangle. You can see that this angle down here is a right angle. And I've already measured that this angle right here, which we'll call A, is 38 degrees. Measure that with a protractor like this. So the saying that you've probably heard before is so ka toa. And this is an easy way to remember the definitions of the trig functions sine, cosine, and tangent. So sine is the opposite over the hypotenuse. And in this case, referring to A, that would mean the opposite angle to A, the furthest side, or the opposite side to A, the furthest side away from it is 2.1 inches. And the hypotenuse is 3.4 inches. So if we wanted to calculate that out, it would be 2.1 over 3.4, which is about 0.62. The cosine is the adjacent, which means next to, over the hypotenuse. So in this case, the adjacent side to A is 2.7 inches, and the hypotenuse is still 3.4. Which, when we round it, equals about 0.79. And now the tangent to A is opposite over adjacent. So in this case, that would be 2.1 over 2.7, which is about 0.78. These are just approximate numbers for a couple of reasons. First of all, I measured these and I rounded my answers to the nearest tenth of an inch. And then I divided those things and rounded them again to the nearest hundredth. And also because when I measured the angle, it's probably not exactly 38 degrees, though it is pretty close to exact. Okay. Before I move on with these, let's think a little bit more about what these functions are, because they are functions. You can see that we're sort of putting in an input and getting an output. So the domain of a function, or the input to a function, what are we putting in here? What type of quantity is the input to the function? And what are the possible values that we could put within these functions based on these definitions, based on how we sort of figured out what it means to be the sine of this angle A? The domain, the possible values, are angles from, and looking at this, the smallest angle we could possibly have here, a really, really skinny right triangle, could get really close to 0 degrees. Or if it was tall and skinny the other way, we could get close to 90 degrees. So the domain of this function sine is angles between 0 and 90 degrees. And the same thing is true for cosine and tangent, because they all take in the same angle. It's one of the non-right angles in a right triangle, so that is always going to be between 0 and 90 degrees. For the range, let's think about what possible values we could get coming out of this function. The three possible values that we saw for these three functions were 0.62, 0.79, 0.78. But if we had a different looking right triangle here, think about what are the smallest and or largest possible values you could get based on these definitions of the ratios of the sides. Okay, so for sine, it's the opposite over the hypotenuse. And we know that the hypotenuse is always the biggest side. If it was a really skinny right triangle, we could get a opposite side that was really, really small, and our answer would be close to 0. If it was tall and skinny the other way, then the opposite side and the hypotenuse could be almost the same length, and our ratio could be close to 1. So the range is numbers, not just angles, but numbers, from 0 to 1. No matter what weird triangle you make, if it's a right triangle and you're looking at the opposite over the hypotenuse, you're going to get a ratio between 0 and 1. And the same thing is true for the cosine. If you think about it, the sine of this angle, opposite over hypotenuse, is the same as the cosine of this other angle here, because for this angle, this side would be the adjacent and not the opposite. Or you can just think about if we were to change the shape of this triangle but keep it a right triangle, we could get a really small adjacent side, or we could get an adjacent side that is almost as big as the hypotenuse. So again, it's going to be numbers from 0 to 1. This is not true for tangent. We're not guaranteed that the numbers for tangent, that the number on the bottom is bigger than the number on the top, because we're looking at the ratio of the opposite to the adjacent side. So for example, I could draw a triangle that was really tall and skinny, and the opposite side could be much, much larger than the adjacent side. So because I'm talking about lengths, all my answers still need to be positive, but I actually could get something close to 0 or as big of a number as I want from the tangent. So the range for tangent is numbers from 0 to infinity. These domains and ranges are based on the definitions up here that are all within a right triangle. During this lesson, we are going to expand a little bit beyond just looking at within a right triangle. So these things will change, but I want to make sure we have a strong understanding of where we're starting from first. Okay. So there's a reason that these functions only take the angle as an input and nothing else. And that's because they don't actually depend on the size of the triangle. If I cut a differently sized triangle with the same angles, they would have a special relationship that has a certain name that you might remember from geometry. They would be similar triangles because they have the same angles. And an important fact about similar triangles is that they have equal ratios of side lengths, even if the side lengths themselves are not equal. So let me show you what I mean. I'm actually going to take this triangle and cut it to be a different size. It doesn't matter what size I'm going to cut it to, but I'm going to cut it so that the hypotenuse has a length of exactly 1 inch. So I'm going to measure 1 inch along the hypotenuse here. And I'm going to cut this down to size so that I have a smaller triangle with the same angles, the same ratios of the sides, even though each of the side lengths individually will be different from what we started with. Okay. So I'm folding this so that it lines up here. That just guarantees that my angles will be the same because this line will be parallel to this one. And I'm going to cut my little triangle here. As best I can. Okay. So now I have a new right triangle with the same angles that I started with, but all the side lengths are smaller. We know what the length of the hypotenuse is. The length of the hypotenuse is 1 inch. I'm actually going to take this down. I can use the fact that the ratios are the same to figure out what this side should be and what this side should be. Sine of A is still going to be this side, which I'm going to use a lowercase a, and cosine of B, or cosine of the angle A, is going to be the adjacent over the hypotenuse. So think for a second about how many inches long is this side and how many inches long is this side. Because I'm taking the ratio with the hypotenuse, and because the hypotenuse is 1, that means that to get the same ratio, this side is just going to be the 0.62 that I got from calculating the sine of A. And this side should be the 0.79 that I got from calculating the cosine of A. That's because now my hypotenuse is 1, so my opposite over hypotenuse is going to be 0.62 over 1, or just 0.62. The cosine of A should still be 0.79, so that means it's 0.79 over 1. So once I cut the hypotenuse to be 1, this side length is just equal to the sine of the angle, and this side length is just equal to the cosine of the angle. Let me just double check that these numbers that I got from measuring the sides are at least close to what the calculator would tell me should be the sine of 38 degrees, etc. So I'm in degree mode. Sine of 38 is indeed closest to 0.62. The cosine of 38 is indeed closest to 0.79. So the numbers that I got from measuring the triangles match up with what the calculator tells me should be the sine and the cosine of 38 degrees. Okay, good. All right. So now, because this triangle is pretty small, I'm going to draw it a little bit bigger on this coordinate grid here. And I'm going to use each box to be 0.1 inches. So this over here is going to be 1. and 1 inch. So I know that my width is 0.79, so that's going to be almost a 0.8. And I know that my height here should be 0.62. So that's going to be right here. So I went over to 0.79 and up to 0.62 using this scale that I drew. Now I'm going to draw this triangle. So this angle here that's starting from the origin should still be 38 degrees, which it pretty much is. Great. Okay. So here's my angle A. And the coordinates of this point are 0.79, 0.62. Or another way to write these coordinates would be the x-coordinate is now the width here, the cosine of A, and the y-coordinate is the sine of A. Okay. I'm going to draw other triangles like this for a few different angles. But we know that for what we're starting with here, all those angles are going to be between 0 and 90 degrees. So why don't I do one that's 45 degrees? Here's A38. Let's see. So sine of 45 degrees is 0.71, and cosine of 45 degrees is also going to be 0.71, because the 45 degree right triangle is isosceles. The two sides are the same. So 0.71, 0.71, that's right here. If I wanted to draw a new triangle here with an angle of 45 degrees instead of the 38, it would look like this. And the coordinates of this point up here would be 0.71, 0.71, or another way to think about that, oops, I don't need that line, is cosine of 45, sine of 45. Okay, let me do a skinny angle, something that's a fairly small angle, and let me also do one that's close to 90. So let me do cosine of, how about 15 degrees is around 0.97, and the sine of 15 degrees is around 0.26. So I'm going to go to 0.97, that's almost a 1, and then 0.26, that's going to be right about here. So this should be a triangle where the angle is 15 degrees. There we go. Okay, and let me also try an angle that's somewhere in here. So why don't we do, I don't know, 65 degrees. So I'm going to do cosine of 65 is 0.42, and the sine of 65 is 0.91. So I'm going to go to 0.42, 0.91. That would be right here. So all of these triangles have a hypotenuse of 1 using the scale that we have on here. And their side lengths then are the sine and the cosine of that angle, their other side lengths. So this is cosine 65 degrees, sine 65 degrees. This one is 45. You get the idea. And it's important to remember that all these angles are measured from the positive x-axis here. So if you look at the shape that these dots are making, and I could do a few more to fill it in. If we were to connect these dots, the shape that we would get is an arc, a part of a circle. So let me actually try to connect these here. And we say that this is part of the unit circle because it has a radius of 1 and its center is at the origin. And the coordinates of points on this circle, using the angle measured from the positive x-axis and going counterclockwise, are the sine and the cosine of that angle. But this isn't a circle, right? It's only a quarter of a circle. So let's extend the circle. Let's take our circle and let's make it go all the way around. I'm going to use an easy thing to remember, which is that 0.6 and 0.8 is on the circle. It's a 3, 4, 5 right triangle. So just help me put in some dots here to make it easier to draw it around. Oh, that's not bad. 0.5, 6.8. Did I do this right? Yeah. Okay. Oh yeah, this one's all the way down here. All right, not too bad. So this is the whole unit circle. So we might want to think about not just the coordinates of the points in this first quadrant, but the coordinates of points in all 4 quadrants. So we call this quadrant 1. And because we're measuring our angles starting from the positive x-axis and going counterclockwise, let's call this one quadrant 2, quadrant 3, and quadrant 4. All right. So far the sine and cosine are able to give us coordinates of points on the circle in quadrant 1. And these are the same thing as saying the side lengths of these right triangles. If I want to find out the coordinates of a point in quadrant 2, we've got a couple of options. One way I can think about it is I can draw a right triangle and I can measure this angle that is called the reference angle. From any quadrant, you can take your point and draw a line from the origin and then just draw an angle between that line and whichever part of the x-axis is the closest. And that's called the reference angle. And that will give me a triangle. And I tried to draw this one so that it was 45 degrees. So then I could use the rules that I know the hypotenuse is 1, and I could find these lengths using the sine and cosine of 45 degrees. However, that's not going to give me these coordinates exactly, because you can tell by looking at it that the coordinates here should be a negative x coordinate and a positive y coordinate. So when you're dealing with these reference angles, you can use the triangles and the sine and cosine to figure out the sort of number part of your coordinates, but then you have to think about visually which quadrant does it fall into to decide on the positive or negative sign. So in this case, because we're in quadrant 2, you can see that the x coordinate should be negative and the y coordinate should be positive. I already found the sine of 45, it was 0.71. So this is going to be negative 0.71, negative cosine of 45, and positive 0.71. Pretty soon we'll learn about how to calculate these numbers exactly in terms of square roots. Okay. So this takes a little bit of extra thinking and picture drawing, and we will do more practice with understanding the relationship between a reference angle and then the coordinates of the point that kind of go with whatever the actual angle is. The actual angle that I'm talking about is still measured from the positive x-axis. So the angle that goes with this point on the circle is not 45 degrees, because the angle that goes with 45 degrees, or the point on the circle that goes with 45 degrees, is this one, since our angles should start from the positive x-axis. So the angle that actually goes with this point on the circle is not 45 degrees, but 90 degrees plus 45 more is 135 degrees. This is not in the original domain and range of our sine and cosine functions. But because we now have this entire circle to understand angles with instead of just right triangles, we can say that the coordinates of the point that go with this not 45 degree number, but 135, starting from the positive x-axis going counterclockwise, the coordinates of this point should be still the cosine of 135 and the sine of 135. These expressions make no sense in the context of a right triangle. We could not have an angle of 135 degrees in a right triangle. But we can ask the question, if I start from the positive x-axis and I go 135 degrees counterclockwise along the unit circle, where do I end up? And the answer to that question is the cosine of 135 degrees in the x-coordinate and the sine of 135 degrees in the y-coordinate. If I type in cosine of 135 degrees, I do get negative 0.71. I don't know if you can see that. There we go. So, because of the unit circle definition, instead of defining it in terms of a right triangle, we're defining the cosine of an angle as the x-coordinate of that angle when you go that far around the unit circle, and the sine of the angle as the y-coordinate of that angle. This matches up perfectly with the triangle definition between 0 and 90 degrees. When we did our 38-degree triangle, we figured out that the sine and cosine from measuring the triangle, that matched up perfectly with the coordinates of this point on the unit circle. But the great thing about this definition is that it doesn't require the angles to be between 0 and 90. Instead, they can really be any angle, and this results in outputs that instead of being between 0 and +1, we can now have negative results for sine and for cosine. Think about where we might have negative results for the sine of an angle. Okay, so my new definitions for sine is the y-coordinate of our point on unit circle. The cosine is the x-coordinate of our point on unit circle. And we haven't really talked about the tangent much. And that's because the tangent really comes from whatever definition of sine and cosine we're using. In our original triangle definition, the tangent was the opposite over adjacent. That's the same thing as sine over cosine because the hypotenuse could cancel out. That's going to be true here also. The tangent is going to be our y-coordinate over our x-coordinate. The domain of sine, the new domain, is any angle, and this is true for all of them. And the new range is -1 to 1 for sine and cosine. And then because sine and cosine individually could be either negative or positive, the range for tangent is now -∞ to infinity, or all real numbers. It's okay. All right, thanks for tuning in, everybody. I hope this was helpful. Feel free to ask me any questions through the different ways that are listed on Canvas if you need help.